Yesterday, limits at infinity. Today we finish up section 12.4. Limits of sequences. It's pretty much almost like the same thing, identical. So, my limits of sequences. I take a look at the sequence a sub n equaling 1 over 2 to the n. Let's write down the first 5 terms. A1. That's it. 1/2. 1 over 2 to the first power. A2. 1 over 2 to the second power. A3. So here by writing out the first 5 terms, we come up with 1/2, 1/4, 1/8, 1/16, and 1/32. So as n increases without bounds, so as n gets closer and closer to infinity, where's my sequence going? To what number? 0. Absolutely. If I take the hundredths term, the thousandths term, it's getting smaller and smaller and smaller. We say it is converges to 0. And our limit notation, limit as n approaches infinity of 1 over 2 to the n is equal to, I was going to put 42, but 0 works just as well. Right? So that's how it is. And see that it is, I'm not trying to add these up, just my nth term n approaches infinity. As we can see in this case, it goes to 0. So, limits of our sequence, if an is a sequence where f of n equals a sub n, for every positive integer n, then we can write this as the limit of our an, same thing as the limit of our f of n as n approaches infinity, which is just some number, right, or L, wherever that limit is approaching. So, again, this works hand in hand with our limits at infinity, same thing at our sequences, because we're looking for the nth term as n approaches infinity. So in this case, we want to find the limit of the sequence an, which equals 2 to n plus 1 over n plus 4. So again, we're looking for how am I going to find this? Stare at it until divine inspiration takes over and I have the answer in my head. No. Plugging 0. Oh. You guys see what I mean. So what do I do? Sorry? Okay. The bottom one looks better than the top one? No? Divided by the highest term? Yeah. What was Stephen talking about? So as we did in the example, we had a dividing out technique pretty much where we take the highest term, highest power term of our denominator, right? In this case, as you said, would be n. So I can do something like right? Simplifying I get that limit as n approaches infinity of 2 plus 1 over n divided by 1 plus 4 over n. The limit as n approaches infinity of 2 is the limit as it approaches infinity of 1 over n. 1. N 4 over N. What is it that Stephen was talking about? Comparing the powers. I take a look. What is the degree of my polynomial in the numerator? What about the denominator? So here we have the case where n equals m. So when n equals m, what is my horizontal asymptote?
Leading coefficient of the numerator over leading coefficient of the denominator.
Somebody has this down pat. Now, absolutely, our horizontal asymptote would just be, as Chris said, our ratio of our leading coefficients. And in this case, that would be 2 over 1, or just. This technique is a lot more important. Why? What did you have to memorize to do this? What did you have to know to do this problem here? You have to remember to just divide by the what? Highest power term in the denominator, right? Yes? What about using this one? You have to remember all three cases. You have to remember, okay, if n is less than m, if n is equal to m, if n is greater than m, what happens? 2 years from now, 1 year from now. Hopefully you still remember that. But it is a lot, this is why this is a nice technique to know as far as, hey, I'm just dividing by the nth term. If you do know the n equals m, n is less than m, n is greater than m, looking at those horizontal asymptotes, that is definitely a lot faster and a lot more efficient. So it's a good idea to know both techniques. If you don't use them a lot, you probably will forget that comparing with your, which way does it work. Whereas if you say, hey, I remember to divide out by that largest term in the denominator, and go from there, that is a useful tool. So, if you guys know it, you can use it, right? So as far as here, find the limit of the sequence. You didn't go back there.
Here. Oh. Is it there?
That's what you said.
Oh.
How'd you come up with that, Steve?
The numerator is less than the denominator.
So, and you can show your work. Here, I am showing my work. Don't just put down 0, folks. Don't just put down does not exist. Don't just put down, right? In this case, it's even said since the numerator is less than the denominator, so this implies now that I have my limit. Is equal to 0. If you don't remember that, again, we would divide each term by what? N squared. Absolutely. Divide each term by n squared, and you'll find out that everything in the numerator goes to 0, and in the denominator I have a 1. 0 over 1 is 0. However, in this case, the only work we had to show was write down something like n is less than m. Right? Which method should we do? Up to you.
So I'm comparing.
Okay, so what am I comparing here? Or what do I get?
They're the same, so this is 4 over 10.
Absolutely. Taylor said, comparing our powers here, you can see I have a second degree over a second degree. So we know that this is going to give us, again, looking at my horizontal asymptotes, our leading coefficient of our numerator, of our highest term, our leading coefficient 4, denominator, my leading coefficient of 12, 4 over 12 are just. Again, if I wanted to, I can divide each term here by n squared. I'm going to come up with that exact same thing. In this case, when I divide by n squared, here I'd get that reduced to a 4, a 12, and this 5 over n squared just disappear to 0. Both ways get you there. There's not one method that is better than the other. One is probably going to stick with you a little bit more than the other, though, as far as remembering. Question? Can I do any of those methods here? Can do what?
Versus
Well, can I use any of the techniques that we have? Should I divide by the highest power in the denominator? Can I go ahead and compare powers? So as both Megan and Chris were saying, what can I do? What is n plus 1 factorial over n factorial? We had that on our last test. Factorial, I'm just multiplying all the integers all the way down to 1. So my n plus 1 factorial over n factorial is the exact same thing as just n plus 1. So now my limit of the sequence is just the limit of n plus 1 as n approaches infinity, which is what? Here. 42. Why did you say so? So as n grows larger and larger, as n approaches infinity, where's n plus 1 go? Sebastian? Absolutely. The limit of n plus 1, right? If I choose larger and larger numbers, 5, 10, 5 million, 5 billion, 5 trillion, right? It's growing without bounds. It's approaching infinity, which means my limit does not exist, right? Because again, my limit has to approach a number. Infinity is not a number, it's a constant. All right? Questions on that? By the way, let's back up this one. Could I have, used, I asked before, could we have used any of those techniques? Can we have used the dividing by my highest power, the denominator? No. Can we use the comparing of my powers? Valerie? How so? I had one more term, absolutely. I have one more term, or excuse me, one more factor in my numerator than I do my denominator, don't I? Because I'm multiplying 1 always up to n in the denominator, and then I'm throwing in one additional n, or the n plus 1, but one additional n in the numerator. So I actually do have a higher degree polynomial in my numerator, don't I? So, use your observations, right? So, alright, how about this one? That one we won't be able to do here. Do we just do a Hail Mary and try to come up with an answer? Let you guys ponder that. What are those two little thinking caps? See some of you starting off pretty well. Most of you need to secure that thinking cap a little bit tighter. Write out the first three terms, see what you get. See if that gives you any inspiration. Perhaps you can graph it. So my A1 would be what? Negative 1 over 1, so negative 1. My A2? Negative 1 squared over 2. Negative 1/3. 1/4. So what's going on here? It is doing some sort of oscillation type stuff, right? But is it converging anywhere? Let's see. How so? Isn't it going back and forth between positive and negative?
Yeah, but it's smaller and closer to 0.
Absolutely. As Stephen said, both the positive and the negatives are growing smaller and smaller and smaller in magnitude. Well, it doesn't matter, positive and negative, it's just getting smaller and smaller. If we were actually to graph that, now we have that little dampening effect type stuff, right? Where it's fluctuating between my positive, oscillating between my positive and negative. But that height, that distance is getting smaller and smaller and smaller, basically approaching 0. So in this case, I couldn't use any of those techniques as far as dividing by my highest highest power term in the denominator, nor by comparing my n over m. But in this case, just by observation. You can see sometimes just writing out the first two terms and say, okay, I can see it is approaching or converging to this particular number. Questions? Very strange. Okay. Find the limit. There was some ghosts in the snowstorm. I showed you. Okay. So, find the limit of the sequence. Someone says it's OG something older than you. Find the limit of the sequence. What you guys tell me? I treat this as two separate problems, or is it just one, or what? What do I need to do here? I can't really separate it, but again, here I'm looking for my we have two different ways of looking at this, right? One where we can divide by the highest power term in my denominator, right? And the other one is what? Comparing what? Even already told us comparing what? Coefficients. Comparing the powers. Comparing my powers in my numerator and denominator, right? As far as is n equal to m, is n larger than m, is n less than m. Do I know the powers? Do I know what's in my denominator? What term do I have there? What degree polynomial? In my denominator. It's the third degree. 6 times n to the third power, right? I have a third degree polynomial. Do I know what polynomial, what degree I have in the numerator? Well, without doing any work, do I know?
No.
Yes. Okay. It's a third degree as well. How many times am I multiplying n? 1, 2, 3. I know I have a third degree polynomial in that numerator. So I can do a couple different things. First of all, I know that the denominator is just 6 times n cubed, so 6n cubed. In that numerator, I can multiply all that out, can't I? It's not difficult. Two binomials and then multiplying by 5 times n, so do we need to? Because I already know in my numerator, I have a third degree polynomial, right? Which means all I'm going to do is what? Take a look at the leading coefficients. So how do I find the leading coefficient in my numerator?
All the coefficients of n.
Just as Stephen said. So if I take a look at my 2n times n times n times 5, I come up with. So Stephen said, just take a look, multiply my n's, and then if I have any constants or coefficients out in front like we did here, I'm going to have 10n cubed plus some other terms, right? Do we concern ourselves with those other terms? No. Because here, again, we're just looking at our leading coefficients. Let's just give ourselves 5/3. If you are unable to see that leading coefficient was 10 times n cubed, you can just multiply it out, right? As far as our two n plus 1 times n plus 1, using our FOIL technique, right? Times n times 5, you're going to come up with 10n cubed plus some other terms as well. Questions? Let's go now, folks. Don't wait until Tuesday. Enjoy.